Hello, Tanya Laird here, and welcome to part 1 of lecture 13 of ENGR 231 Engineering Statics. In this portion of the lecture, we're going to start looking at a topic that I really enjoy, and that is shear and bending moment diagrams, one of my actually favorite parts of statics class. So let us look at what we've looked at, or let us review what we have learned previously. Let's look at what we've seen previously. First of all, in lecture 12, we learned how to find internal forces at a single point. Internal forces at a single point. So in other words, we would have a beam or a framework or something like that. Maybe something like this. And we would then have a couple loads on it, have some sort of load distribution on it, whatever it may be. Cut this, and then look inside this thing. Maybe here. Something like this. And you'd have reaction forces here. And then we would ask, okay, what kind of axial force, what kind of shear force, and what kind of moment has to exist within that beam. Actually, we used N for axial force in our previous video, so I'll use that N here as well for normal force. Again, so that's what we looked at last time, but all of this is based on finding the force at the internal forces at a single point. What we're going to look at today is finding the forces at any point, or really finding forces at some point x. Essentially finding forces at any point, or finding forces as a function of x. Now, I'm not going to be concerned with columns today and axial forces. Instead, I'm going to be looking primarily at shear and bending moment. So essentially what we're going to be doing is we are going to be taking beams, and we're going to be cutting them at certain points, and we're going to be solving for all of the forces on them in terms of x. And forces on them, I should probably say forces in them rather than forces on them. So let's look at a very basic example of what I mean by this. A very basic example. Let's consider perhaps the simplest case of this you could have, which would be a simply supported beam with just a uniform load across it. It's not going to get more simple than this. Or simpler than this. This is about as simple as it's ever going to get. So, let's say we have a load of 2 kips per foot across the top of this thing. Two kips per foot, which means, of course, that each foot of the beam is going to have 2,000 pounds, or actually 1 ton, imposed upon to the top of it. So 2 kips per foot. And, I don't know, maybe we can give this thing a length of 10 feet, why not? And, so all this is given. And I want to find, let's say, the shear and bending moment diagram. And bending moment diagram on this beam. Okay, so I'm going to go through a set of formal rules after this, but I just want to illustrate the basic idea of what I'm talking about. So first of all, the first step is going to be to solve for the reaction forces, and because this is a symmetric beam, I can show a global Freebody diagram very easily. There's going to be no horizontal reaction forces on this. Hopefully that's fairly straightforward. And I'm not showing it cut yet. I'm just showing it in its entirety, a global Freebody diagram. And if I wanted to solve for these, I could show an AY and a BY and etc. But I think by this point you can see that if this is a symmetric beam, again, if we have a uniform load across it and it's nice and symmetric, at least in terms of vertical support, it's symmetric, there has to be 10 kips of force here and 10 kips of force here. So 10 kips and 10 kips. And we'll have a total distributed load, or the same uniform distributed load of 2 kips per foot. 2 kips per foot here. No change from above. Now imagine I want to know, so previously what we saw is, or in lecture 12, what we looked at was trying to cut this thing at a point and solving for the shear and the moment at that one point. But what I want to do is, instead of trying to cut this at, say, 2 feet from the left, or 5 feet from the left, or 6 feet from the left, what I want to do is cut it at any location. Or in other words, I want to cut it in terms of x and see what kind of things happen. See what kind of shear and moment develops. So let's do that. I'm now going to cut this, not at some known location, but I'm going to cut this at some point x. I'm going to cut this at some point x. So in other words, I'm going to get the shear and the moment functions, or I'm going to get the shear and moment not as just set values at a certain point, but shear and moment as functions of x. Okay, so let's go ahead and draw out a Freebody diagram here. Maybe I'll draw it a little bit bigger than it should be. Now I'm going to draw this a little bit bigger than these other ones because I want to be able to draw some the equivalent point load, that kind of thing. Actually, maybe I don't want to make it quite as big as the original. I want to show that it is reduced a bit. So what do we have here? We're going to have a 10 kip load over here, and then a distributed load here, a 2 kip per foot load. But the length of this cut is not now, again, it's not a fixed length, rather it is of length x. This thing is now going to be of length x. So instead of being 2 feet down or 5 feet down, we are now x feet down. And I'm going to construct this all in lengths of feet for this problem. But you can also use metric if you wish, or you can use kips, or you can use pounds, or whatever unit you would like, as long as you're consistent from problem to problem. Now, so I want to show what kind of internal forces are revealed by this cut. I could show there's axial force, but there's obviously not going to be any axial force on this because I don't have any vertical, I don't have any, horizontal load. And also, as we saw in the previous lecture, this does not mean that this beam necessarily has to be purely horizontal. I drew this as horizontal, but as we saw last time, if we had a slope beam, we handle that by transforming the loads so they're all either along the axis of the beam or perpendicular to the axis of the beam. And same thing if we have loads that are coming in at an angle. We split those up into loads that are parallel and perpendicular. Perpendicular loads contribute shear and moment, while parallel loads that are parallel to the axis of the beam, those contribute to your axial force. Okay, but back to the shear and moment, which is we focus mostly on shear and moment because those are the real tricky ones and have really interesting integral relationships and things like that. Axial force is more just axial force. It doesn't really build upon itself to build up shear, or basically we'll learn later that there is a integral relationship between load and shear, and an integral relationship between shear and moment. And so that builds like layer by layer. Axial force, it's more just, well, that's the axial force present in the column. It's a little bit simpler. So here, we're going to have some V, and that's going to be V. I'll just put a V sub x to show that it's V at some point x. And then I'm going to have mx, the moment at some point x. Now, also notice I am using the sign convention we used last time. So again, as a reminder, this means positive shear, or what means, let's discuss again as a reminder, what is positive shear? Positive shear is where you have a downward force on the right-hand side of a member and an upward force on the left-hand side of a member. This is positive shear. This is negative shear, where you have a downward force on the left-hand side of an element and an upward force on a right-hand side of the element. So again, you cannot just look at an arrow. It's very tempting to sort of take a blind zero-thought approach and say, oh, I see an upward arrow, therefore things are positive. Unfortunately, that's not correct. You have to look at it not just what direction the arrow is pointing, but where it is on that element. A downward arrow on the right-hand side of the element is positive shear, and a upward arrow on the left-hand side of the element is also positive shear. Alternatively, another way you can think about it is if your shear arrows kind of are moving in look like they're moving in a clockwise direction, that's positive shear. If it looks like they're moving in a negative direction, in a counterclockwise direction, it's a negative shear. Or you can kind of think of another way to conceive of this is that it's almost like their sign conventions go a little bit opposite moments, but even moments are a little bit trickier here because we know this is positive moment when you have bending like this. Although this is at least easier because it's causing this thing to bend in kind of a smiley face pattern, and smiley faces are positive and happy and positive bending. So positive bending, we're doing happy beams, gonna paint happy trees, summon Bob Ross, etc. Anyway, okay, that's very incredibly stupid joke even for me. So I'm going to show the equivalent point load on this thing. Now, we know that when solving for the forces on the edge of an element, we can use the equivalent point load method. And what that means is, again, we'll replace this distributed load with a point load that is the same total magnitude and positioned at the centroid of this distributed load. So what is the equivalent of this? Well, previously we could say if it was 2 feet, we would just multiply 2 feet times 2 kips per foot and say, oh, that's 4 feet. Or sorry, oh, that's 4 kips. But we don't have that luxury here. Instead, we have to say that this is just 2 times x. The equivalent point load of this distributed load here, 2 kips per foot of length x, is simply 2x. And this thing is not located at a firm distance, but instead it is at a distance of x over 2. X over 2 from the left-hand side. X over 2. So we are then going to use this, this as a force in terms of, we're going to treat this as a point load or use this point load when calculating our shear and moment. So I'm going to do the exact same thing I did previously where I looked at summing forces in the y direction and summing moment. Summing forces in the y direction will give me my shear, and summing moments will give me my internal bending moment. So I can do a summation of forces in the y direction. And again, as a reminder, when we're doing this, just because I have assumed this is to be in the positive state of moment and shear, but that need not be the case always. Again, when you have arrows that are, when we actually, just because something, when I set these up, I did assume a positive state of shear, but when you actually do the sum of forces, all that matters is whether an arrow is pointing upward or downward on your cut section. So I'm going to have 10 kips, and that's positive because it's pointing upward. Then I'm going to have minus 2x. Minus 2x. And this is the equivalent point load of this entire distributed load, again at some point x. And then minus vx, and this equals 0. Then if I solve this for vx, I get that vx is equal to 10 minus 2x. Or if I wanted to, I could say v as a function of x, shear as a function of x, is equal to 10 minus 2x. And this would be in units of kips and feet. Or I could just say kips here. So that is the shear as a function of x. I now have the entire shear equation. I can just put in any point x and solve for the shear. Then I can do a balance of moments. And again, just like I did previously when I looked at shear and moment at a single point, I like to solve for those at some point x. I like to take moments at some point x, and again, the whole reason for that is, as I alluded to in the previous lecture, if I include this vx here, or let's say I sum moments about here, the left-hand side here, if I do that, the nice thing is I don't have to include the 10, or I suppose I could do here as well, but the nice thing about doing this is that I don't need to include the vx, which is itself a function of x, so that makes things a little bit simpler. So I'm going to sum moments about point x here, and then I would have, well, first I would actually have the moment, mx. Then I would have a negative moment caused by that 10 kip force. So minus 10 kips, but times a moment arm length, not of a known length, but of length x feet, or just x. So it's still a negative moment because clockwise rotation, but the moment arm length is simply x. Then plus the force, which is going to be 2x, and then times a moment arm length of x over 2. This whole thing has length x, and again positive because counterclockwise rotation about point x here at the end of our beam. And so again, the load is going to be equal to a magnitude of 2x, and the moment arm is going to be equal to a length of x over 2. And all of this will then come to 0. So mx minus 10x plus x squared is equal to 0, and mx is then equal to x squared, or actually that would be 10x minus x squared. And this is our moment function. So we now know the moment at any location here as a function of x. Interesting. We now know the moment as a function of x. And what do you notice about these two? Stare at these equations for a bit. We have 10 minus 2x and 10x minus x squared. Hopefully it should be fairly straightforward or fairly clear what I'm getting at here. Now, if this was in class, a physical class, I would actually go and ask everybody what is the relationship between those two. And hopefully I'd get a bunch of people screaming at me, well, not hopefully screaming at me, but a bunch of people saying, obviously, the relationship between these is that we have a derivative and integral relationship. The moment is an integral of shear, and the shear is the derivative of moment. Now, if you just saw one of these, you might think, oh, maybe that's just a coincidence. But in fact, that is not a coincidence, as we will see later on. So I want to explore this. And so, again, we got that v of x, and this would have units of, I should probably put units here. This would have units of kip feet. This would have units of kip feet. And what else? So let me write this down over here. V of x is equal to 10 minus 2x, and m of x is equal to 10x minus x squared. If I copied those correctly, 10 minus 2x and 10x minus x squared, yes. So if I were to plot these out, I would then actually get the shear and moment diagrams. Shear and moment diagrams are a fancy way of saying just drawings or plots of the actual shear and moment functions. So let's look at a few of these, or let's look at this. Well, this is going to be a linear equation, and if I do v here, v is a function of x. If I put in 0, I'm going to get, let's see, if I put in 0, I'm going to get 10. And the beam is 10 feet long. So 10 minus 2 times 10 will be negative 10. Negative 10 is negative 10. So we're going to have a linear plot of shear here. We're going to have a linear equation for our shear function, and it will start out being positive on the left-hand side, and it'll be negative on the right-hand side. Fairly straightforward, hopefully. And then the moment, however, the moment is going to be not a linear function, but a parabolic function. Now, it's not as easy to just put in points here, although I suppose it is. So if I put in, first of all, I know it's going to be concave down, and I could start by just getting some known points. If I put in 0, it's going to be 0, 0, 0. If I put in 10, well, let's see, that's going to be 100 minus 10 squared, or minus 100. So that means at 10 feet, it's also going to be 0. 10 feet, comma 0. And then if I put in 5 here, well, let's see, that's going to be 50 minus 5 squared, or 25. So that will be 25. 25. Or maybe I could say 5, comma 25. And this would be m in units of kip feet. M in units of kip feet here. And this would of course be a parabolic function. This would be a parabolic function. And because the values are positive throughout this beam, this is going to be in positive bending, or nice, happy, smiley face bending. This is going to be entirely in positive bending. That makes sense. This whole thing starts out at 0, and the thing is concave down through its entirety, so it would make sense that this would be positive bending. Also, it is no coincidence that these line up. as we'll see in part 2 of this lecture, there is a derivative relationship between shear and moment. In fact, I can skip ahead a bit and mention that shear is the derivative of moment, as we saw previously. It's hard to escape these derivative relationships. They're actually working through some of these equations, so it's hard to kind of escape them. However, we'll look at that in some greater detail in part 2 of this lecture, but that is the basic idea. So you have this derivative relationship, and in turn, because there's a derivative relationship, the slope or the value of this graph is the slope of this graph. So every time shear is equal to 0, the slope of the moment function is equal to 0, or in turn, wherever this is 0, you'll have a maximum or a minimum in your moment function. Okay, but that's the basic idea of shear bending moment diagrams. Now, to actually get these, they can be more complex, and there actually are some other techniques you can use beyond just solving for cutting it at a point x. But in this lecture, I'm going to focus mainly on doing this as a function of x. But I want to give you a few ground rules. I call this, now in other, you may see in some of my other videos for mechanics of materials and structural analysis, I actually formally break these down into shear and bending moment diagrams by 3 methods. The method of cuts, the method of sections, solving by integration, and by inspection. But we're going to call this, I would refer to this one as solving for V&M diagrams by the method of sections. So I can maybe title this here, V&M by the method of sections. V&M diagrams by the method of sections. So the general idea that we're going to look at, or the general process, is going to be 1, solve for external reactions first. Solve for external reactions first. 2, convert all loads into components that are parallel and perpendicular. Maybe let's write it out, and perpendicular to the beam axis. To the beam axis. 3, effectively cut the beam at some location x. And I should probably mention here, only perpendicular loads only perpendicular components contribute to V&M. Contribute to V&M. To shear and moment. 3, the third step, is going to be to cut the beam at some location x. We're going to cut it at some unknown location x. And then 4, apply equilibrium. Apply equilibrium equations. Apply equilibrium equations to solve for all unknown, to solve for your shear and moment. And I suppose if you wish, you could also do axial force. Shear, moment, and axial force. And axial force. And this is the basic method. This is the main method, but then in the next slide, I'm going to discuss a few caveats, a few difficulties, and mainly that comes down to discontinuities. Discontinuities and coordinate systems. Okay, that's the main method though. All right, so step 2, or not step 2, item 2, I want to talk about discontinuities and coordinate systems. Maybe I'll talk about discontinuities first. First of all, we saw previously that the load, the distributed load here, is going to have a profound effect upon the shear diagram. And notice we had a continuous load here. We had a constant load. And when I say continuous load, I mean the mathematical definition of continuous. You can have also a load that is all sorts of crazy shapes. A continuous load is the mathematical definition of continuous. You can have it as crazy as you want, but it has to be, it fundamentally has to be one continuous function. Now, you could have a piecewise function that had no breaks and valleys. Well, actually, you know what? I should probably say a continuous load. Well, I guess we could do something like that, yeah. You could have a load as complex as you want, but it has to be continuous if you're going to avoid discontinuities. So a load like this is a very complex load, and to solve for actually using the equivalent point load method on this would be very difficult indeed. You would pretty much be forced to solve this one using integration, which is something we'll look at in the next section. But you would still be able to handle it as one chunk. However, if you have a discontinuous load, let me show you what happens when you have a discontinuous load or discontinuous beam. Imagine you have let's say you have a beam that is still simply supported, but instead of having a distributed load, and I'm going to go ahead and draw the V and M under this. And I suppose we can work through this later, but for now, I'll take my word for it that the shear and moment diagrams will look like this. Your V and your M. Imagine you have a single point load in the middle here, P, and then maybe if this is symmetric, let's say this is in the middle, this would be P over 2 here, and P over 2. What your V diagram ends up looking like is something like this. The P over 2 causes it to immediately jump up on the left-hand side to P over 2. Then it remains constant over to the middle load. Then it drops down by P to negative P over 2. And then it remains constant until you get to the right-hand side, where you jump back up to 0. And then moment, actually let me draw this moment a little bit lower than that. I want to give myself some room to write. The moment is going to be continuous but not differentiable. Again, using mathematical definitions of continuity and differentiability, this is going to be a linear function and a nice straight linear function, if I can manage to draw a straight line for once in my life. And let's say this would be equal to PL over 2. PL over 2. And that would be positive throughout it. And we would have a positive shear here and negative shear here. And this is assuming the beam is of length L. If the beam is of length L. Now, looking at this, again, as if this is a PL over 2, but notice what happens here. When you have this point load, previously the load was nice and continuous, or in the previous example, the load was nice and continuous. So the load was smooth all the way across, and that doesn't, again, continuous does not mean constant value. You can have this curve here is a continuous function, but there are no sharp jumps in the load. The value continuously changes, but there is no point where it is at one moment it's, you know, a kip per foot, and then a millimeter or a micrometer to the left, it's now, you know, 2 kips per foot or something like that. Or I probably shouldn't use metric and English together, but oh well. There are no sudden jumps in the load. But here, there is a sudden jump in the load. Here, there's 0 load, 0 load, 0 load, 0 load, 0 load. Suddenly a whole bunch of load P, then 0 load, 0 load, 0 load, 0 load, all the way to the end. This represents a discontinuity. And so, whenever you have discontinuities in your load, you're going to have discontinuities in your shear function, and then discontinuities, or more often breaks in differentiability in your moment function. So again, discontinuities in load and you know, I should really say load or support equal a discontinuity in your shear and moment functions, in V and M functions. So let's look at this. in the V and M functions. So let's consider some examples of discontinuities. The first big one would be the ends of beams. The ends of beams, or the beam ends, or begins, or I guess begins or ends. Those are discontinuities. Now, those are fairly obvious because the beam just stops there, starts there, so you're not going to be analyzing shear at some point outside the beam, so that's fairly obvious. 2, point loads or point moments. And point when I say point moments, I also mean couples. Point loads and point moment, points loads, point loads, and point moments / couples. So if you have a beam, every time, maybe I can go ahead and draw something like this. You know, I'm going to make this a little more colorful. I'm going to circle in purple, I think. So let me show some loads on here in red. Here and here maybe, and then maybe a couple here, and a couple here. Well, in this case, again, back here, I would have discontinuities at the beginning and the end. And of course, we would still have discontinuities at the beginning and the end here. I'm just showing you examples of discontinuities here. Point loads, those represent discontinuities in beams. And couples also represent discontinuities in beams. Now, couples are not going to cause discontinuities in the shear function, but they are going to cause discontinuities in the moment function. Because shear is fundamentally related to translation, and couples and moments are fundamentally related to translation. So then, 3, let's consider another example. And what else could I talk about? Let's see. Yes. Distributed loads. What about them? Maybe I should say we're distributed loads. Where distributed loads start, stop, or change function. Or change function. So let me show you one beam that will maybe include all of these. It's a fairly complex beam. I probably wouldn't give you a beam quite this complex on an exam. These can get quite fun though. So maybe something like this. Let's say we have something kind of like this. And I'm going to circle the X locations which would have discontinuities. So it looks kind of like we have so maybe I can just, and discontinuities again from the loading itself, not from the supports or from the beam ends. So here you would have a discontinuity because the distributed load is starting. Here you would have a discontinuity because the actual value of the load doesn't change there, but the function of it does. In other words, if I were to describe this load function, I would basically need a 3-part piecewise function to describe it. One region from here to here, one from here to here, and one from here to here. Again, here, the actual value of the load doesn't change, but the function of it does. So I would need to go, that would be counted as discontinuity, and so would this here. And these would be examples of discontinuities that come from loads. Again, the actual value of the load doesn't need to change. I would call this load continuous, but not I would call this continuous, but not differentiable. And since taking shear bending moment diagrams, or creating them fundamentally involves differential relationships, we have to separate the beams there. And then 4, I will say supports. Now I'm going to draw a beam that's not simply supported, but I think you can get the idea. Well, actually, maybe I'll just draw something like this. Now, oftentimes, or for all the beams I've drawn so far, everything these are all simply supported, and so the supports lined up with the ends of the beams. But that need not be the case even for a simply supported beam. even for a statically determinate beam. If I started adding all sorts of supports, then you're gonna get all sorts of discontinuities. But even for a simply supported beam, even for a statically determinate beam, this beam here is statically determinate. It has 3 reaction forces that's completely statically determinate. And I would have one discontinuity here at this support, and I would have another one here. Now, if your support is right at the end, you're just going to double dip with here, and so you don't need to count that twice. We're looking for the actual number of discontinuities. Doesn't matter if they're overlapping. What we're ultimately looking to do is figure out how many places we need to divide our beam into. So the whole point of looking at all these discontinuities is the discontinuities give you the boundaries of your zones of analysis. Provide the boundaries of the zones of analysis. Of zones of analysis. The discontinuities provide the boundaries of the zones of analysis. And let me show you what I mean by that. So what we're fundamentally looking to do is we want to create functions. We're trying to create functions in terms of x, but in this case here, we could solve for the entire beam as a single function of x. But we can think of this, just think of this mathematically. All of this here, this diagram here, was fundamentally, all this was fundamentally based on this load function. And so if the load function, now I started with a simply supported constant load because that's the simplest case. It's very easy to understand here, to give you a very basic example. But it's easy to see that if I change the load function, all of these numbers would be different. All of these equations would be different. And so if on one beam, the actual, okay, back up. If I change this to 4, then obviously all this would change. If I put this as 2x, then all of this would change. And so if it was 2x, the load itself would be more triangular than constant. And so everything there would change. But if the actual load itself changes at different locations on the beam, then of course your load functions will change. Your load function will change. If your load function is changing along the beam, then of course at different locations your shear and your moment will change along the beam. Those functions will. So fundamentally, the discontinuities previously discussed, or on the previous slide, directly relate to discontinuities in the V and M functions, in the shear and moment functions. In the shear and moment functions. Those are directly and inextricably related. And so, for example, or not for example, let me just say basically, these discontinuities, so because your V and M are going to have discontinuities, your V and M are piecewise functions. Your V and M fundamentally are going to be piecewise functions. And what do I mean by that? Well, let's say we had a beam that, maybe you had something like this. Maybe I'll draw something out. Maybe I'll give some dimensions to this. I'll make it interesting and have that pin and roller, but not being simply supported. Maybe I'll have a point load here, and then a distributed load from here to here. So I want to go, let me go ahead and give the dimensions too. Let's say it's 4 feet from here to here, here to here, maybe another, let me just do some proper dimension lines here, or proper-ish. Let's say here, here, and here. Let's say it's 4 feet from here to here, 4 feet from here to here, 4 feet from here to here, and 6 feet from here to here. So let me look at my discontinuities. I would have one here because the beam is starting and there's a support there. I would have another here because I have a point load. The location at any point load is going to be guaranteed to be a discontinuity. Again, point loads or point moments are always discontinuities. I have another one here for this support here. Then I have a discontinuity here because my distributed load starts. And I have another discontinuity here because my distributed load ends and the beam also ends there. So even if this distributed load was maybe ending a foot to the left, well, I would have one discontinuity here and another one there. So my V and M functions are going to end up looking like this. My V of x, and notice I'm going to take these for a consistent x. I'm not going to solve through this one because would be a bit long, but I will illustrate the idea. You would have some function when x was between 0 feet and 4 feet, and that would cover this region here. You would have some other function, some other v function when x is between 4 feet and 8 feet. That would describe the shear from here to here. You would have some other function, shear function from here to here, and then again that would describe the shear from here to here. So that would be from 8 feet to 12 feet. Notice I am using the same coordinate system throughout. And then I would have some function from here to here. And that would be, I guess if I add 12 to that, that would be 18. So some function from 12 feet to 18 feet. And M would be the same. In fact, I could write all this again, but again, it's just going to be some M of x as well. M of x, and they would not be the same functions, but there would be some V of x and some M of x. They would all share the same boundaries. So your sheared moment ends up being very different equations, but they end up having the same boundaries. And sometimes I refer to this, or I frequently refer to these as zones of analysis. For this particular beam, we would have 1, 2, 3, 4 zones of analysis. Next, I'd like to look at a few notes on coordinate systems. Notes on coordinate systems. What I'm going to tell you to do is in this class, 0 is, at least for a beam that you're, well, again, you're going to be redrawing these in their own local coordinate system anyway if you do have a sloped beam. And so for this class, 0 is on the left-hand side. It's always going to be on the left-hand side. And x increases to the right. Always. No exceptions. And so, and in each zone of analysis, the x coordinate does not reset. Does not reset. Does not reset. So what do I mean by this? Well, let's say you have a beam like this. Maybe a nice simply supported beam. A point load here or something. And maybe we have another one here or something like this. And let's say this was 4 feet, 4 feet, and 4 feet. It's very tempting when doing a free body diagram or doing a cut here, for example, to try to redefine your x coordinate as this point here. When you're working through that, I see people try to do something like they try to maybe cut it into type and completely isolate the piece or something like that. Maybe like try to cut it. Maybe like sometimes when analyzing this zone here, I'll see students try to make a diagram that's like this with a P here and then a V here and an M here, and then try to put an X here where X is now defined 0 from this point P. That is very wrong. That's not what we're going to be doing. When I'm going to be analyzing this zone here, I'm going to have the same left-hand side that I've always had, and I'm going to have a point P here, and then I'm going to have some the cut at some location X. But X is not 0 from the boundary of the cut, or the boundary of the zone of analysis. X is still always measured from the left-hand side of the beam. We do not redefine the 0 every time we get this, because again, the whole point of this is that we're trying to create a unified set of piecewise functions that have a unified coordinate system. And if you're trying, the reason this will be really important is when we get to boundary conditions, which we'll see in the first example that we look at, the first longer example that we look at. And really, this is absolutely essential. So do not, looks like a P, do not redefine your coordinates. If you do, you'll make me sad. So don't do that. Do not do this. Do not put your 0 anywhere except right the left-hand side of the beam. Again, assuming you're looking at this in a local coordinate system. If your beam is a column that's vertical, well, what's the left-hand side? I don't really know at that point. Along the beam's axis, depends on how you're looking at it. But if you have a drawing of a beam and the beam is horizontal, 0 is on the left-hand side, always and always, forever and ever, amen. It never moves. It is fixed upon the earth. It shall never move an inch. It is some metaphor for something that doesn't move very much. It is the immovable force, and not even the unstoppable. Sorry, it's the unmovable object, and not even an irresistible force shall move it. So do not move 0, 0s. Always on the left-hand side, no exceptions. Anyway, and to the right is positive. I get really excited about this stuff. Okay, maybe I can look at an example here with a discontinuity in it. All right, so let's consider a beam. And maybe I can do something like this, something relatively simple. Let's say I have a beam like this. And maybe there's going to be a distributed load. You know, I'm going to make this a little bigger, actually. So I'm just going to I think I'm going to work through one basic example. There are further examples in your text, of course. And also there's the one we looked at previously, a very easy example, but to demonstrate the concept. So illustrate the idea of how we work with discontinuities. So here, let's say the following is given. Let's say we have a beam, and I think I will go with that interesting beam, where it's simply supported, but it's not cantilever, and it's statically determinate, but it's not simply supported or cantilevered. And I guess we've done all the other ones in English, so maybe I'll do this one in metric. So let's say and I want to keep this relatively simple. So here, let me think about that. Yeah, this is gonna be fine. Let's say I have a 10 kilonewton load, and then a distributed load from here to here of 5 kilonewtons per meter. Actually, let's do 3. 3 kilonewtons per meter. And then let's say this thing has dimensions. Oh, I don't know, let's say this is 2 meters and 3 meters. Actually, I don't want to repeat that. So let's say this is, I don't want to repeat a 3, so maybe 4 meters and 3 meters here. All right, did it again. Let's say 5 meters, 4 meters and 5 meters. One of those things. Okay, so first thing I'm going to do is get my external reactions, the AX and AY. Let's call this point A and this point B, AX and AY and BX and BY. Now I'm going to go ahead and just say that the AX is 0 because we have no horizontal force on this beam. So I'm going to go and, oh, I should probably state what I'm looking for. Find the V and M functions and diagrams. The V and M functions and diagrams. All right, so we have this. Now, Again, the first step is going to be to find the reaction forces. And let's see here. I'm going to have an AY, and then I'll have a BY here, and a distributed load of 3 kilonewtons per meter. Uh, 3 kilonewtons per meter. And a point load on the end of 10 kilonewtons. And then the beam lengths, or the relevant lengths here, are going to be 4 meters and 5 meters. 4 meters and 5 meters. Now, when doing this, I still want to use the equivalent point load method. And the equivalent point load of this distributed load, again, for the purpose of finding reactions, I can use this, or internal forces at the end of a beam. I can say that this is 3 kilonewtons per meter, and there's 4 meters, so we have a total load of 12 kilonewtons. And this distance is going to be at the center of the distributed load, which, again, if it were something like a triangle, we would put it 1/3 from the edge. But if it's a uniform load, that's just going to be halfway across, or 2 meters. 2 meters. So I want to get both AY and BY. I'm going to do this by balance of moments. So sum of moments about point A. If I do a sum of moments about point A, again, I don't need to consider the actual distributed load anymore because I've replaced that with an equivalent point load, and that's what I'm going to use for my my vertical force and moment calculations. But again, I'm going to do this once for the distributed load, or for the global reactions. But then after that, when I'm looking at each individual cut, I'm going to have to look at it a little differently. Okay, so the sum of moments about point A, I'll have the negative moment caused by the 12 kilonewton force, so 12 kilonewtons, with a moment arm length of 2 meters. Then I'm going to have BY. Oh, that's a negative there, negative moment. BY is going to be a positive moment because of counterclockwise rotation. Or I can just say 4 meters times BY, or 4BY. Then I'll have a negative rotation, or a negative moment from the 10 kilonewton force, so minus 10 kilonewtons, times total moment arm length of 9 meters. So this is not going to come out to nice even numbers, and I'm just going to go ahead and do this as some ugly decimals. Times 9 meters equals 0. So then 4BY, or I could just say BY, is equal to 24 plus 90 divided by 4. 24 plus 90 divided by 4. Actually, it may come out to something decent. 24 plus 90 divided by 4. Oh, never mind. That's not right. Okay, that's fine. Why is that? Okay, that's fine. So let's just say BY is 28.5. So that's actually not too ugly of a decimal. 28.5. 28.5 there. Or sorry, not 2.5, 28.5 kilonewtons. I always end up slipping back into kips. Kilonewtons. 28.5 kilonewtons. Next, I'm going to do a summation of moments about point B. And that I'm going to use to get AY. Summation of moments about point B, I'll have the negative moment caused by AY, negative AY, times a moment arm length of 4 meters. And now my 12 kilonewton equivalent point load will be generating a positive moment about point B. So plus 12 kilonewtons times a moment arm length of one half the distance, or 2 meters. And again, that's a positive moment because of counterclockwise rotation. And then this 10 kilonewton load will be clockwise, or a negative moment. So negative 10 kilonewtons times a moment arm length of 5 meters. And this all then comes to 0. And so let's see, if I bring AY over here, and I could say this would be 24 minus 50 equals AY over 4. So 24 minus 50 divided by 4. And I get that AY is equal to negative 6.5 kips. negative 6.5 kips. So AY is actually not an upward force. It is a downward reaction force. And really this kind of makes sense. If I imagine a rotation about this point here, what's happening is this large point load at the end is wanting to cause things to this whole beam to kind of rotate over like this. And this moment here, or this reaction here, is actually holding the thing down, kind of nailing it down and preventing it from rotating upward. It would otherwise like to sort of pivot about point B. All right, so we have that, negative 6.5 kips. And I'm going to go ahead and draw out a global free body diagram again. I don't necessarily need to, and you really wouldn't need to for homework or an exam or something, but I just want to really spell out what's going on here. And I'm going to also use this to circle any of my discontinuities. So I have a distributed point, or a distributed load, not a distributed point load, but a distributed load from here to here of 3 kilonewtons per meter. Then I have the 10 kilonewton load on the end. And then I have dimensions of 4 meters and 5 meters. 4 meters here and 5 meters here. And 5 meters. And then I have reaction forces. I have a downward reaction force here of 6.5 kilonewtons. And here I have an upward reaction of 28.5 kilonewtons. And if you wanted to check these, you could again look at the summation of forces in the vertical direction. These together come up to a sum of positive 22, and this is basically negative 12 and negative 10. So the positive 22 minus 12 minus 10 comes to exactly 0. So this is an equilibrium. Okay, and this is basically our simplified or a very basic rough global free body diagram. Now I'd like to look at the discontinuities. I purposely chose this beam or design this problem to have, I wanted to at least demonstrate the idea of solving my discontinuities, but I wanted to keep things relatively simple. And, if I give you a beam with, 8 discontinuities and it will be there, we're going to be there for quite a long time solving that. And this video is already long enough. So I want to circle this here. I have one discontinuity here because of the end reaction. And you can see here, this is fundamentally why reactions or supports are discontinuities. We call them we tend to call the things that we impose on the beam loads, and these reactions. But nature is nature. Nature's going to do what nature's going to do. Physics is physics. And a force, whether it's produced by a reaction, something that's actually holding a structure down, or a machine down, etc., or imposed loads, forces are forces. And anytime you have a point force, or a point couple, or a couple I should say, you are going to have a discontinuity. So I have one discontinuity here, both from the support and from the actually it's from a whole bunch of things. From the reaction force, from the start of the beam, and from the start of this distributed load. Then here, I have discontinuity from both the end of the distributed load and from the location of this reaction force. And then I have another one here, which is from the point load on the end, and also the end of the beam itself. So fundamentally, I'm going to end up with something like this. I'm going to use 2 different zones of analysis, and I'm going to get a v of x that is some function from x is between 0 feet, or if I can manage to write equations properly, 0 feet, or not feet actually at all. Recording this a little too late at night, I see. 0 meters, x, and 4 meters. And another zone of integration, another piece of the piecewise function, that would be between 4 meters and x is between 4 meters and 9 meters. Again, notice I am not committing the cardinal sin and redefining my my coordinate system when I get over here. I move from 4 to 9. I don't just go from 0 to 4 and then jump back to 0 because I've redefined my coordinate system because I don't know what I'm doing. I keep my coordinate system constant. This is a common question I get a lot. A common question, or something that's often brought up, is should it be less than or equal to, or greater than or greater than or equal to? Well, there are cases where the numbers might actually make sense, but there are cases where it will be a continuous function but not differentiable. But fundamentally, oftentimes I prefer using the less than, not the less than or equal to, because if I go to the, where's that example of the, where did I draw that here? Showing the breaks here. When you have a point load, notice you have a sharp jump in the shear function. This shear function would be like v of x equals, this would equal like v of x equals, let's see, from x is less than L over 2. This would be, actually, I should probably put the function first. P over 2 when x is less than L over 2. And negative p over 2 when x is greater than L over 2. Notice, this function is really only correct between 0 and L over 2, the halfway across the length of the beam. And this function is only valid until you get to right after L over 2 and right before the end. Again, right at that point, you get a sudden jump. Effectively, it's like having a function of infinite slope or something like that. Or you could have positive or negative infinite slope. I guess this would be negative infinite slope from here to here. Looking at rise over, if you try to do a rise over run over that, you get a something over 0, which would be either positive or negative infinity. That basically has a negative. It basically has a negative infinite slope. In other words, at the point of the discontinuity, or at the point of the point load p, the shear function itself is undefined. Now, this function is a little bit different. Your moment function would actually be the value from the right would actually equal the value from the left, so it would be continuous. So we could get away in that case. We could actually get away with using the greater than or equal to and less than or equal to, but it's probably better practice just to use the less than rather than less than or equal to, because then if you had a discontinuity in the moment function by, say, a couple, then that would not work. Then you actually would have a jump in the moment value. And then m of x is going to equal some function when x is between 0 meters and 4 meters, and some other function when x is between 4 meters and 9 meters. And 9 meters. All right, so what else do we have? Or how else do we want to proceed? Well, the next step is going to be analyzing each of these in their own zone. So it's generally best to look at one zone at a time. And so I'm going to first look at the first zone, which is when x is between 0 meters and 4 meters. So I'm going to draw out the Freebody diagram, cutting this at some location x. So let's do that. You know what, I'm going to try to sort of split this up like this. I'm going to do one when x is between 0 and 4, and then I'm going to try to put this on one slide, or this part of the problem on one slide, 4 meters and 9 meters. So again, I'm cutting at some location x, and this one's going to be very similar to the first example I worked through, or at least this portion of the problem is going to be very similar. We're going to have a 6.5 kilonewton force. Then we'll have a 3 kilonewton force distributed across the top. Three kilonewtons. And then we'll have, again, I'm assuming positive shear of V, some V at x, and I'm assuming positive moment, mx. And I do want to use the equivalent point load of this distributed load, and that's going to be, well, again, this entire thing is going to have a length of x, so I probably should draw that out. This portion of the beam will have a length of x, and the equivalent point load will have a magnitude of 3 times x, 3 kilonewtons per meter. And actually, I probably should write not just 3 kilonewtons, but 3 kilonewtons per meter there, if I want to do this nice and consistent, nice and proper. 3 kilonewtons per meter. And I can just say this is 3x. And then this is at a point that's at the centroid of the load, which would be 3x. This would be x over 2. X over 2. So the load itself has a magnitude of 3x and is located at a distance x over 2 from the left-hand side of the beam. Again, all of this is going to be solved in terms of x. So I'm going to do the same thing I did previously, where the sum of forces in the y direction, and I will have I have made a critical mistake. Maybe you saw that. That 6.5 kilonewtons should be pointing downward. Gotta make sure you get everything balanced and set up properly. So I will have negative 6.5 kips. I did it again. Kips, not kilonewtons. Every time. Every time. I'm just too much of an American. Anyway. Negative 6.5 kilonewtons. And then minus 3x. Again, that is the magnitude of the equivalent point load of just this in terms of x. And then minus Vx. Minus some Vx. And this is then all equal to 0. So Vx, if I solve this, negative Vx, let's see. Well, actually, I could just say, if I bring this over here, I can just say Vx, again, just from x equals 0 to 4, is going to be equal to, if I bring this over here, it's positive, then I multiply by negative 1, it's negative again, negative 3x minus 6.5. Minus 6.5 kilonewtons. Then, to get the moment, I'll do a sum of moments, and again, I'm going to take this about x. Sum of moments about point x. And I could say then, I'll first have the actual mx, the moment at that point, and then a positive moment from the 6.5 kilonewton reaction force, because that's a counterclockwise rotation. So plus 6.5 times the moment arm length of x. Then this is going to be this will cause a positive moment as well, plus 3x times the moment arm length of x over 2. Times the moment arm length of x over 2. And that's it as far as moment balance, and all this equals 0 because, of course, this is statics class. So mx mx plus 6.5x plus 1.5x squared is equal to 0, and mx, again, just in this first region, mx is equal to 1.5x squared, 1.5x squared plus 6.5x, plus 6.5x. And so now we have the moment function and the shear function in this first region. Next, on to the same thing, but in the second region. So I'm going to draw out another Freebody diagram, but this time I'm cutting it at an x that is in the second region, between 4 and 9. So let's go ahead and draw this out. Now I'm going to include the downward 6.5 kilonewton force. And I'm going to then put the upward 28.5 kilonewton. And I will have the 3 kilonewton per meter force. Then I'll have some unknown v of x, vx, v at some point x, and mx. And let's label some dimensions. These are, I do recommend labeling dimensions on these. So this is at x, right? This at point x? No, we don't want to do that. That's the exact opposite of what we want to do. We have to keep x as from the left. So embrace your inner Bernie Sanders and keep everything from the left. Oh my god, that's a stupid joke even for me. Wow. Politics jokes. That one's bad even for me. Okay, so we have a point x here, a distance x from the left. Now this distance is not, this distance here is not going to change. This is just the actual length of this distributed load. That's going to be 4 meters. But if, so we got to do a little subtraction here. If it is x over the entire beam, or not the entire beam, to wherever our cut is, the distance from here to that cut is going to be x minus 4. X minus 4. And I'm going to use the same equivalent point load. Now, this one here, I can just use the total. This is 3 times 4, 3 kilonewtons per meter times 4 meters of 12 12 kilonewtons. And I know via centroidal distances that this is at the middle of the load, or 2 meters. And if this from here to here is 2, the moment arm for this equivalent point load to that point there is going to be there. This is going to be x minus 12, or sorry, x minus 2. X minus 2. This is going to be x minus 4, and this is going to be x minus 2, and we'll use that when we're doing moment calculations. Okay, but first of all, our first step is just going to be to sum for forces in the vertical direction to get our shear function. So if I sum forces in the vertical direction, I will have negative 6.5 kilonewtons, and then plus, well, actually, let me just go from left to right. Negative 6.5 kilonewtons minus 12 kilonewtons. So that's negative 6.5, that's the reaction on the left, minus 12, that is the equivalent point load of the distributed load. Then plus 28.5, plus 28.5, and then I would just have minus Vx. And all of that then is equal to 0. So if I add these up, negative 6.5 minus 12 plus 28.5, I get just 10 here. 10 minus Vx is equal to 0, or Vx in this region, when x is between 4 and 9, Vx is just equal to 10 kips. Vx is equal to 10 kips. Then I can take a summation of moments in the about point x again. And this one's hopefully fairly straightforward. I will have I'm just going to go from, I'll have 3 things here. Well, first I'll have my mx, the actual moment at point x. I will have the positive moment from the 6.5 kilonewton force, so 6.5 kilonewtons, times the moment arm length of x, so k kilonewtons, not kips, kilonewtons, times the moment arm length of x. Then I'll have a positive rotation from, or positive moment from this 12 kilonewton force. So I'll just say that's 12 times the moment arm length of not x, but now x minus 2. It's x minus 2 from here to here. So, and maybe I can just, you know what, I'm just going to simplify this by saying, save some room by saying 6.5x and 12 times x minus 2. 12 times x minus 2, and then plus, or actually minus in this case, minus 28.5, minus 28.5 times the moment arm length of x minus 4. Notice we don't try to double count our distributed load, we only count we just use the equivalent point load method, and we only have to consider it once. And this all equals 0 because this is a statics class. Okay, so let's go ahead and get this. So mx, or let's simplify this, plus 6.5x plus 12x plus 12x minus 24. I'm just multiplying across 12x minus 24 minus 28.5x, and then 28.5 times 4. That comes to 114, but plus 114 equals 0. So mx, 6.5 plus 12 minus 28.5 is negative 10. Mx minus 10, or actually minus 10x, and then minus 24 plus 114. So minus 24 plus 114 is plus 90, equals 0. And then mx, if I move this to the other side, mx is going to be equal to, mx is going to be equal to 10x minus 90. So I could then, I then want to rewrite these as unified piecewise functions. So v as a function of x for this problem. Well, let me get the first 2 regions here, or write these out with the regions first. I'm gonna have one function. When I have one function was x is between 0 meters, and actually I'm going to move this a little bit over. 1 when x is between 0 meters and 4 meters, and 1 when x is between 4 meters and 9 meters. And same thing with the v. I'll move this a little bit further over to make sure I have enough room. And please don't be confused by the v of x and the vx subscript. There's just two ways of saying the same thing in this context. This is going to equal something, or this equals something when x is between 0 meters and 4 meters, and something else, another function when x is between 4 meters and 9 meters. And this first one is negative 3x minus 6.5. And this other one is 10. This one here is 10. And this one here is 1.5 x squared plus 6.5x. Uh, 1.5 x squared plus 6.5x. And then this here is just going to be 10x minus 90. 10x minus 90. 10x minus 90 here. And notice, wait a minute, did I get that one right? Something's not right here. This should be derivative of this. We have a mysterious negative here. What happened? We need to check this. There is some error present here. So we know that these should be derivatives of each other, and the fact that there is a negative here is a bit disconcerting. That these are negative and this is not is a bit disconcerting. Now, the algebra here looks right. Let's see. At least when this is set up properly. So minus 6.5. Let's see. Minus 6.5. Did I get? Let's see. mx plus 6.5 times x plus 3x times x over 2. Ah, there's the problem. That should just be, I apparently don't know algebra. That is just minus 1.5x squared minus 6.5x. Okay, that explains it. And so this is minus 1.5x squared and then minus 6.5x. So that is often a very quick check you can do. And actually, I probably should have done that before. It should have popped out earlier. I guess I was rushing to get along to the next section or the next zone of analysis. But that is the basic idea. And I could plot this if I wished. So let's see, the v. So these are my shear and moment functions. Then my v and m diagrams are really nothing more than just plotting these. V is a function of x, and this is in kilonewtons for this example. So let's see here. The initial value is going to be negative 6.5, and I'm gonna want to plot both of these on between 4 meters and 4 meters and 9 meters, or 4 meters and 0 to 4 and 4 to 9. So I'm gonna go ahead and usually when I draw these, they're not like super precise. They're just simple sketches. Now, in ye olden days, if you were doing this before a lot of calculators and stuff, you would actually maybe do this using high precision, things like protractors and that kind of thing, using very precise analysis and that kind of thing, precise measurements, everything to scale, etc. And m is a function of x. This is in units of kilonewton meters. Kilonewton meters. And then what I like to do is, I like to show a little dotted line, just as a trace line to show where where the 4 meter and where the bounds of integration or the boundaries of the zones of analysis are. Now, and I use these to try to connect the shear diagram to the moment diagram. It's very common for me. And in fact, I might even erase this and show a trace line down here so they can all start and end at the same point, or as close as I can get drawing this freehand on a computer screen. And if you're wondering how I create these videos, if you want to look up something called a Wacom Intuos tablet or something like that. It's basically a drawing tablet. That's how I create all these. These aren't created like on a touchscreen or anything. They're created on a touchscreen tablet. They're actually created on a separate writing pad. Not that you'd know it based on the quality of the handwriting and drawings, but anyway, it's neither here nor there. So here, and then we have the same, I should probably put the same dimensions, the 4 meters and 5 meters. and 5 meters here. So the first thing I'd like to get is maybe the coordinates at the bounds, or at the start and end. So this is going to start at negative 6.5. If I put in 0 in for shear, I'm going to get negative 6.5. Negative 6.5 here. Then, let's see. So we're going to start at actually, I want to put that a little bit higher to try to be consistent. Negative 6.5. These don't have to be to scale, but I try to keep them at least reasonably consistent. And then when I put in 4, that's going to be negative 12 or negative 18.5. Negative 18.5. Negative 18.5. So again, if I put in 0, I get negative 6.5. And if I put in 4, I get negative 6.5 into this first region. So we have a linear equation from 0 to 4. And it's going to drop from negative 6.5 down to, if I can manage to draw a straight line, down to negative 18.5. Then I'm going to have a sharp jump because in the second region, we're going to be up here at 10. We're going to be way up here at 10, and we're just going to jump. And this is fundamentally why we have to use the less than rather than the less than or equal to, because there's a discontinuity in the shear function. And then we are actually constant all the way till the end, and then we kind of drop back it down. That's kind of, we haven't really looked at that yet. That drop down will be caused by the end load there. But again, you don't necessarily need to include that. That's just, but that's for the, usually I just always like to bring my shear and moment diagrams back to 0 at the end. And that's positive. Then the moment, let's see, at 0, this is going to have a value of 0. Simple enough. No great surprises. Then if I put in 4, so negative 1, I'm going to throw this in my calculator, negative 1.5 times 4 squared minus 6.5 times 4, and this comes to negative 50. So I'm going to go down to negative 50. Negative 50. And so we're starting at 0, but we're going to just descend, and this is going to be parabolically, but also notice the slope on this, or the coefficient on this. That tells me, because this is a parabola, if I take the second derivative of this, I'm going to get just negative 1.5, and that tells me the concavity. I know, just based on what I know from calculus, I know this entire function is concave down. So that means I'm not going to have a curve like this. Again, I'm not going to have a curve like this. I'm going to have a curve that's concave down. So I do try to get that, at least if I'm doing sketches, even if I'm just doing sketches, I do try to make sure I at least have the right concavity on my basic sketches. So that we're going to parabolically descend from 0 to negative 50. Then, will we have any jump? Let's put in 10. Well, we can see this here. 10 times 4 is 40, minus 90 is negative 50. So we actually don't have any discontinuities in the moment function, but the actual function does change. The actual equation of it changes. And so we're going to start here at negative 50 at x equals 4 meters. And then when I go to x equals 9 for x equals 9 meters, I'll be back up at 0. And that's going to be a linear function. That's going to be a linear function. So this thing starts out at 0. Let's start again. This starts out at 0 and it's going to end up at 0. And we'll have something like this. And so we actually have negative bending moment throughout. In the previous one, we had positive bending moment throughout. In the first example, we had positive, or the first simple example, we had positive bending throughout. And in this one, we have negative bending throughout. All right, so this is definitely longer than what I try to do with the statics lectures in this lecture series. And normally I do try to break them up into sort of normally I would try to teach this as a theory video and a examples video, but I think I really wanted to start out with a very basic example of illustrating how this process worked. Then I wanted to discuss some of the caveats, or actually formally introduce the method, introduce some of the caveats, and work through a slightly more complex example. Now, this is still much, much simpler to the more complex things you can see for these. I do teach shear bending moment diagrams in structural analysis, and the ones I give those students are far, far beyond what I give students in this class, especially on exams and things. But do make sure that you're at least able to, for students in my current semester, or in this class the current semester, make sure you're at least able to work through the very basics of these types of things, know how to handle things with discontinuities, know how to break things into zones of analysis, and know how to use equivalent point load methods applied at centroids to solve for the shear moment in different zones by a balance of forces and a balance of moments. Alright, so I think this will do it for this portion of the lecture. Please let me know if you have any questions. Again, actually that probably needs a, I see that needs a little arrow there, okay, by random chance. So again, please let me know if you have any questions. I'll be happy to answer whatever I can. Please let me know if you have any questions. I hope you found this enjoyable. Hope you found this illuminating, or at least hopefully a little bit useful, and or at least hopefully didn't put you to sleep too quickly and maybe got through most of it. Again, please let me know if you have any questions, and if not, I will see you soon for part 2, where we look at the derivative and moment relationships for V&M diagrams, or the derivative and moment relationships between shear and moment. I'll see you soon for that. Please let me know if you have any questions. I'll see you all for part 2 soon, and as always, thank you.